so here we go, talking about a little bit of biochemistry. And so we're starting with electron dot diagrams today, and so you know why all of a sudden we're like into the details is because we went back in time with evolution into the origin of life, and even past the origin of life, and actually we talked about the study of the origin of life. And in fact, there was one guy, Stanley Miller, who what? Tried to create.
I don't like that guy.
He tried to create life by providing all of the known compounds of the day with a little bit of spark in a test
I don't
tube.
like Stanley Miller.
Oh. Sure, he really doesn't care. Okay, I'm not sure if he might have passed. I'm not sure, but I think he did. But the point is, all right, he created from his experiment of using the known compounds of the day, okay, with a bolt of electricity, which would be like, let's say, lightning. He created organic compounds. Organic compounds are compounds that are the smaller of the atoms, and of course they all have carbon in them. But when I say organic compounds, I'm saying covalently bonded compounds, and I want to explain that difference. I know that we had the form, and I know it was very different from everything we were doing, and some people saying almost, oh my gosh, we're doing something totally different. No, we left off with Stanley Miller's experiment, and what did he find? He found, okay, amino acids, nucleic acids. Okay, we're going to study these in great detail. All right, these compounds have what we call nonmetals in them. These nonmetals are the small atoms. And because of their small size that we'll talk about today, they bond in a particular method. So I'm leaving off with the idea that, okay, we're right around before life, and now we're going to talk about the details of life. And so now we're going to spend some time in a little bit of biochemistry, and then we're going to use that biochemistry to talk about the details of genetics, which explains hereditary, which explains chromosomal line theory, which explains the details of why the two chromosomes carry the code and what that code actually is, and how that code actually gets duplicated in the what cycle of the plant cycle. Remember, we have the mitosis or meiosis, a small part of the overall life cycle of a plant. We have the G1, we have the S1, and the G2. Sometimes it circles in G0 and never gets to this phase, the synthesis phase. S1 is where what? DNA, deoxynucleic acid, or deoxyribonucleic acid, which is one of the things that he found. So he didn't find life, but what did he find? He found the molecules that are in life or support life, okay? So we'll never know, we still don't know how life started. Okay, we have our theories, we talked about that, but now we're talking about, okay, what is these actual molecules? Exactly how does the chromosomes get duplicated here? So when I say 2n equals 4, I know that if I ask you to draw that on a test and say, give me, okay, in prophase of mitosis, okay, what the nucleus looks like when 2n equals 4. And everyone should know at this point, how many chromosomes am I drawing? No. You're drawing 8, because during this cycle right here, the DNA is duplicated. So if I said 2n equals 4, I would expect you to draw me 8, okay? And these guys are sister what? Right here. And why are they sister chromatins? Because they're exact duplicates. The DNA was duplicated. Well, what the heck is it? How does it get duplicated? What are the fine details here? Well, that's where we're headed. And that's where we're headed into genetics. Genetics and the fine details of how heredity works and how everything that we've been looking at as a big picture works. Now we're going backwards and flipping that into the details. Okay? So that's why you're studying chemistry, because you don't have biology without chemistry. People say, well, why don't you start with it first? Some teachers do. I don't, because I know that every step of the way, I want you thinking big picture. If I was to start you with the cell, with this and that, you wouldn't be able to do, in my opinion, okay, big picture understanding until much later in the course. From day one, I wanted you to connect to all these different concepts. And as we talk about the details that we're going to start today, I'm still going to keep you to those big concepts. That's the skill. That's what I want you to do for you. So we've talked about this. We've talked about Mendelian genetics, but now we're going to get to how that works specifically. Okay? What are these amino acids? I've been saying they're the soldiers of our DNA hereditary compounds. Well, why? How? What exactly do they look like? What exactly do they do? We're going to get to that. All right? All right. So, any case, moving on. All right? So, that's important links. I really fight to see the link from the first day to the last. So, we're not just jumping into something new. I'm taking you from Stanley Miller's experiment, where, again, he found amino acids, nucleic acids, all things that we call organic. Okay? And the word organic means that they are usually, well, they are carbon-based molecules, okay? And of course, they're special because they generally have smaller atoms, and because of that small size, their type of bonding is important to recognize. So I hope you understand why we're headed that way. Okay, so let's get rid of this, okay? And let's get into the main crux. When you look at the atoms, and I have this up here, if someone was to say to me, you know, give me one table, one piece of information to work with in all of chemistry, I'm going to say, did I hit record or not?
Yes.
Okay, I'm going to say this is my table here, okay? So if I was to have one table, and this was in your,
Why don't they use this instead of like the number thing?
what's that?
Why don't they use this instead of the number thing?
That's a great question. There's a lot of people who take science and want people, and because maybe they learned it memorizing, they teach it memorizing, or they just think it's information. Whereas I look at science as a way to completely understand the world around you. See, I want to teach you a way that you'll remember this. You take chemistry, and we just do chemistry. But chemistry, of course, and biology are constantly what? You know, interacting with each other. That's why you call it biochemistry. But that's not going to work. Okay. But
Is
anyway,
chemistry next year?
what's that?
Is chemistry next year?
If you want it to be, it doesn't have to be. Okay. Some people wait a year. Some people take it as sophomores.
When you take in a grade then?
You would take Regents chemistry. Okay. And some people do great in that, and then they want to come back again. So it's nothing you don't have to. Because people say, no way, AP Chem and sophomore, that's for seniors. Okay, maybe. Not for everybody. Okay. Any case, so this is what I want to give you the visual. When I look at the periodic table, and I know that there's going to be some holes in your understanding. I'm not expecting you to be a chemistry student by 2 lectures in a worksheet. But I want to give you just enough of what this really means to apply it to AP Bio. Most teachers wouldn't go this far. They would just say, here's the rules, and just go with that's how it works, and don't worry about it. Okay? But I want to give you the feeling of why this works. Okay, so first and foremost, okay, it's important to understand that atoms have a nucleus, have a nucleus, and they have an area outside of that. So if I look at an atom, on the outside, we know that electrons exist in shells. They're not actually circular shells, but they're regions of space outside the nucleus. Okay, you're going to find that the nucleus of an atom is a very small portion of the overall atom. If you had, say, Citi Field or Yankee Stadium was the comparative size of an atom, a baseball at second base would be the entire nucleus of that atom. Okay, so the nucleus of an atom is tiny compared to its space, and its entire mass is in that space. A guy named Ernest Rutherford discovered the nucleus, and he said it was mostly empty space. So the entire mass of the atom, and here's the reasoning behind it. Okay, we know that a proton is positively charged, has a mass, and it has a mass of 1, and it's +1. We know that an electron, okay, from other experiments, they give it a 0 mass, but it's actually 2,000 times lighter than a proton, okay, and it's -1. What we know from experiments is that electrons exist in energy levels. Now, to make it simplified, and we'll get into the details another time, these energy levels are based upon distance, and that's not wrong. So energy levels these shells or energy levels, they're not really what? Circular orbits. But we can use that analogy to learn because it still works that way. Electrons that are in the second shell are physically farther away from the ones in the first shell. Electrons in the third shell are physically farther away from the ones in the second shell. That is true. Are they circular orbits? No, but we can use that analogy to learn this, and I will get to those details. So we know electrons exist in distinct shells, okay? And we know as they fill, they start closer and they go out. But inside this nucleus, as I said before, are two things that have mass. There's protons, and then there's neutrons. Neutrons have no charge, but they're also a mass of 1. So when I look at what's in the nucleus, we have protons, and we have neutrons. And of course we have these electrons existing in shells. Okay, now, when you look at an atom, like the periodic table that I gave you for work of home, let's say we take out lithium, all right? And if you look at lithium, okay, and I'm gonna put a piece of paper over this for right now, but I'm gonna get to this in a second. So again, I'm really fighting for you to truly understand what all of this means, not just give it to you and say, hey, you need it, learn it, too bad. I want you to feel it, be one with it. Okay, I know it's kind of strange, and you know I'm strange, so. Okay, so let me just cover this for a second. Okay, so here, I'll make this bigger for those at home. So I've got lithium, okay, and atomic number 3, and there's a 7. Now, in truth, if you look at lithium on the reference table, okay, it's not exactly 7, but we could round it off. So if you take the periodic table that I gave you at home, okay, and look up lithium, we can see that there's a 3 on the bottom, and of course, something very close to 7 right there. Okay, and you say, oh, I don't see that. Well, okay, let's get close, up close and personal. Okay, so there it is. Maybe.
That means that it's second smallest, right?
Second smallest, no. This number is hard to read, but it's 6.941. This is atomic number 3. Okay, so let's rewrite this so we can see it over here. So here's lithium, atomic number 3. Now, we have found out since Dmitri Mendeleev, he was the first one to make his table. That was a table that was on its side and kind of weird. Okay, that the atoms go in order of proton numbers. And we know that different elements are made of different atoms. And what makes beryllium an element that's different from a lithium is that beryllium's atoms have 4 protons, and only 4. There's no other element that has atoms with 4 protons. So what makes atoms unique is a number of protons. So when I write lithium 3, it's almost redundant. By saying lithium, I'm saying we're dealing with atoms with 3 protons. So I write 3 protons. Okay, now, these guys are written as atoms. I say atom, you say neutral. Atom, atom, atom. Okay, you're saying with less enthusiasm every time. Okay, well, neutral means the whole thing is 0 charged. Because if I draw this, we got positive, 3 positives in the nucleus. In the nucleus, it's plus 3. Now, how many electrons exist outside that nucleus for the entire atom to be atom neutral? How many electrons do I need? If each electron is -1.
3.
Thank you. So you have 3 electrons. Okay? And so the lithium atom, neutral, must also have 3 electrons. So that number tells you how many what? Electrons you have if it's an atom.
Neutral.
Neutral. Thank you. All right. Now, of course, electrons don't exist haphazardly. They exist in shells based on distance. Now, in your reference table, they tell you that. They say 2-1. So they're saying in the first shell, the first number, right? In the reference table, it says 2-1. They're saying in the first energy level, there's 2 electrons. I'm going to put them here. I know they don't go in circular orbits, but it's still a good analogy. And 2-1, there's 1 more electron that's in an energy level that's a little farther away. And so when you think about the size of the atom It's based upon the what? The nucleus and the outermost electron. And that, of course, is that's where we get the atomic radius, right there. All right? Now, so the distance between the nucleus. Now, we're not done. Okay? We have the arrangement of electrons. In this case, it's 2-1. Now, look at beryllium. It's got a 4 there. It's got 4 protons. Beryllium's an atom.
Nucleus.
Neutron. I mean, neutral. I messed up my own rave. Okay, now, so beryllium has 4 protons. How many electrons would it have to have?
4.
And we have to put electron into the what? It's 2-2.
So 2 shells.
So the next electron goes here. Okay, if we go to the next element, even though I have it up, okay, boron, don't be one. That's atomic number 5. How many protons?
5.
How many electrons?
5.
Good. And guess what? That'd be 2- what, you think?
3.
3. You get the point. And we end on 2-8. There's something special about filling this second energy level, or filling your energy level and having 8. There's something special. We'll talk more about that. But when you can fill that energy level, that's a thermodynamic pathway that's favorable. It wants to happen. High energy goes to what in nature? Low energy. It's a pathway. Heat goes from what? Hot to cold. Cold doesn't flow. So things that are high energy disperse out to low energy. Well, low energy scenarios for these elements is to fill their shell. Now, hydrogen is on the first shell. Look at the 2. Notice that 2-2, everything starts in 2. The first shell holds 2 electrons, not 8. So hydrogen wants to be stable by having the same number as helium, which is 2. Okay, I'm not done here yet. Okay, so these are some basics you have to have. Now, if you look on this thing, it says 6.941. We're going to round off to 7. This is the mass number. This is the what? Atomic number. We call it the atomic number like the Social Security number. It's also the electron number. Now, who has mass? Electrons, we discovered, are 2,000 times lighter than a proton and a neutron. So they're considered to have a mass that's insignificant to the mass of the atom. Okay, proton has a mass, atomic mass of 1 unit. That unit is hard to measure. It's a comparative unit. And so does a neutron. So neutrons and protons have about the same mass. Okay, so if this is the proton number, and this is the proton and neutron number, because the entire mass of the atom is the protons and neutrons, to get neutrons I subtract 7 minus 3. And that gives me what? 4 neutrons. Now neutrons exist in the nucleus. So there's going to be 4 of these here. Okay, where exactly, who knows? I'm just putting them haphazardly. So the nucleus of lithium is 3 protons, the nucleus is 3 protons, 4 neutrons. Okay? And the entire mass of the atom, okay, is where these guys exist. That's the basics. Okay? Now, just for some fun, ever hear of 7-Up? That soda? Well, that soda, 7-Up, okay, even though it's kind of like been taken over by Sprite. Sprite now does it. What's that? Well, the thing is, they used lithium salts. They used lithium salts to actually flavor the soda. They pulled them from the product because they found out that lithium salts actually are very helpful in treating mental health disorders. They don't want people buying 7-Up and saying, taking another dose of medication. They want to be able to control that. So they pulled lithium salts from the soda. But the scientists or the people who created it thought it was very, very what? Smart of them to call it 7-Up. Why?
There's 7.
Atomic mass of 7 is above the atomic number. Lithium is the salt they use to do it. So 7-Up, the soda, is named after the atomic mass of lithium, as we often write the mass above the atomic number. Okay, so little tidbit of information that's going to get you nowhere in life. At least now you know it. Okay,
Well,
so.
if I'm on Jeopardy, it might be helpful.
Yeah, maybe, yeah.
27.
Okay, so what are we getting back to? So those are some basics. So as we go across the periodic table, okay, as we go across the periodic table, if we're in the same row, we're in the same energy level. That means the outermost electron is about the same distance, okay? And so if I take this off and get back to my chart, okay, What was I after? This is important. As I go across the periodic table, what do I know? That if I'm in the same energy level, same distance, this is +3 in the nucleus. Beryllium is atomic number 4. Boron's atomic number 5, 6, 7, 8, 9, 10. Why are they getting smaller? Yes?
The top radius gets smaller.
Why though?
Because the atomic number increases.
Yes, but the atomic number is increasing as I go down. This is atomic number 3. This is 11. So that's not happening there, so I can't say yes to that. Yes?
They're getting like pulled in.
They're getting pulled in because the size of the positive charge, or we call nuclear charge, is increasing. Now people say, wait a minute, aren't we adding an electron every time though? Shouldn't that cancel off? As I have 3 protons, I have 3 electrons. I have 4 protons, 4 electrons. So, yeah, I'm having more protons, but I have more electrons. Why is it still getting smaller?
Shell.
Well, we're in the same shell. So you're in the same shell if you're in the same row. This is row number 1. First shell, 2 electrons. Row number 2, 8. Okay, and that's where we're going to stay. Yes.
With smaller numbers, or smaller shells attract greater.
They do, but here's the reasoning. Electron is 2,000 times lighter than a proton. So if I give an electron a -1 charge right here, and I'm a +1 charge, so we're equal and opposite. We attract each other because of difference of the charges. Well, who's going to move as I increase in charge?
The electron.
Because it's lighter, 2,000 times lighter. So it's going to move. Okay? So yes. So if you notice, as you go down, we get bigger. Why? People said this already. Yeah, we're adding more shells. So when you look at this, this is important. This is the yin and yang chemistry. We have, as we add more, what? Electrons to small shells. Okay? These electrons, okay, as we add more protons to small shells or small atoms, they have a great ability to attract their own electrons and fantasize about grabbing more. So these guys right here, if you look at the staircase, okay, represent your non-metals. And they have an unbelievable ability to attract electrons. Everybody else here represents metals, and they're bigger. And you can think with me, metals have electrons that are physically far apart from the positives. If the negatives are far apart from the positives, you feel those negatives less. And therefore, these guys tend to lose electrons. Okay? Here's the example I gave you. And I don't know if I gave you the scenario, but I want to give you this. Okay? So there's 2 types of bonding. And we are not going to be dealing with this type, but this is one type of bonding I want to talk about. Okay? Where are we?
I got SB as a non-metal, and it's under the staircase. I can give you the numbers.
No, I don't. Do you have are you just throwing something out there, or do you have a? So we have boron, silicon, arsenic, tellurium.
It's next to.
Yeah. So antimony is not considered to be a non-metal. It's considered to be a metal.
What is a metalloid?
Okay. Now, if I'm saying big atoms
In the back.
and small atoms, what the small atoms good at? They're so good at attracting their own electrons, their nucleus must be good at attracting other electrons. These guys have electrons that are so far away, they don't attract them very well. So these guys tend to what? Lose electrons, and that's called oxidation. That's why metals rust. These guys tend to what? Gain them because they attract them. They have high electronegativity, low electronegativity. That should make sense to you. Now, where is the line? Well, boron, silicon, arsenic, tellurium, germanium, and antimony. I'm sorry, it is a metalloid, my bad. Okay? Those guys are the line in between. They have properties of both. Okay, so they're called metalloids. And our silicon chips that are computers or handheld devices, we have integrated chips. We deal with these guys. We put them in there because they're not great conductors, but they're not bad conductors, and we're able to dope them to make on-off switches. On-off switches are how binary code works. Okay, transistors used to be the first one. So computers work by a binary code. And so these guys have properties of both. But back to reality, okay? This is important. I gave you this. This type of bonding occurred once before. And I just had a piece of paper. I don't know what I did with it. Okay? But in any case, so let's do it this. Let's do this for a second. What if I take a big, like sodium? Where is sodium? Sodium is right here. Now, what's its configuration? You can check in your periodic table. It is 2-8-1. What row is it in? The outermost electron is in the third. Okay? Now, put a small over here. Fluorine. Fluorine would be 2-7. This would be 8. Okay. Now, check it out. Sodium is a big atom. Fluorine, a smaller one. Now, this guy has an electron that's really farther away from the nucleus, easily lost. This one attracts electrons. How small it is. So what's going to happen is, this is exactly what happens. So to leave home, when I leave home every day, I want to leave home as a winner. So what I do with my kids is I want them to have that same feeling. So when I leave, and I did this with my oldest, and I do this now with my youngest. He's a 5th grader.
Kids are up at 4 a.m.
What's that?
Your kids are up at 4 a.m.
Oh, I wake my youngest up. He's got to learn.
This is rude.
And so we have a big rope in my kitchen. And I wake him up. He's crying a little bit, you know. I tell him, be a man, you know, whatever. And he grabs the rope. He knows the deal now. Okay, and we have a tug of war. Now, I don't let my kids win anything.
No.
If they win something, they actually earn it.
Because you're the
I think I
winner.
would run away if my dad wasn't here before.
Sounds like a good plan until you realize where you're going to go. All right, now. All right, so he grabs the rope. I grab the rope. He tries because he knows I'm going to yell if he doesn't try. Okay? And I pull as hard as I can. I yank him. He goes flying. Sometimes he goes into the refrigerator. All right, and he's down for the count. Crying a little bit. He's whimpering. He doesn't like that. So he's whimpering. He's on the floor. Okay, I stand over him and I say, "Who's your daddy?" Now, that scenario, I was stronger than my 5th grader. I yanked the rope away. By the way, I won.
He's like a doll.
Okay?
A doll.
No, I don't do that. I don't do that. I give him gloves. Okay? Now, so what was happening? I was like the nonmetal, the small. I ripped the electron away from him because I have a great strength for electrons. He doesn't. What did I become? 2-8. I'm stable. Low energy now. By the way, I just became negative. What is sodium? Sodium, well, couldn't it gain 7 to get that magical 8? But how is it ever going to gain 7 if it loses electrons? So it loses what?
I have a question.
It loses 1 to become 2-8. You lose a negative, you become positive.
So it has
And,
to, like, stay constant.
and they stick together because negatives and positives stick together. This, of course, is the compound in your toothpaste. Yes?
Okay, if there's, you know how it's 2-8-1 and
Yeah.
and the F is 2-7?
Correct.
How is Na so much bigger if it's only 2 more?
Because it's putting electrons in the 3rd shell. Look where sodium is. It's in row 3. Look where what? Fluorine is. Row 2. Being in the 3rd
I
shell.
think they were in the same
No, this is row 3, 3rd shell. Electrons are. This is the first electron in the 3rd shell. 2nd electron, 3rd shell. This is the 7th electron in the 2nd shell. Going to another shell means you're physically putting electrons farther away. Yes.
Can I have one of those sheets so I can look at it?
Which ones?
That one, the periodic table.
Yeah, definitely you could pass them around if you want. Okay, probably shouldn't do that, but in any case. Now, here's how it looks. Party people, watch. Sodium has 1 valence electron. Valence electron is that electron that is in the outermost shell. We call it valence because that's the electron we care about. See, these electrons, look at sodium. It's got a positive nucleus. It's got 2 electrons in the 1st shell. It's got 8 electrons in the 2nd shell. And now it's got 1 electron in the 3rd shell. The reason why it's bigger than any second row element because it's got the third shell farther away. Now, it's positive 11 in the nucleus, and it's got 11 what? Electrons. 8 plus 2 is 1. These dashes that I'm writing equal the number of protons. It's an atom. Now, party people, this 2-8-1 is what this means. Now, these electrons right here are core electrons. They're closer to the nucleus, which means what? They are attracted to that nucleus so strongly, they're never going to change. It's the ones that are farther away. Think about it. Think about it. I'm positive. You're negative. The closer I get, the more attractive force we have. There's a distance factor there. So these electrons don't feel the nucleus as much. So they're the ones that change in bonding, never the core. So when we do Lewis dot diagrams today, and I'm going to walk you through some, I'm always showing the outermost dot. Okay? Now, what else do we have?
We think, Mr. Gotsky,
Yeah.
the dot sheet too.
You should have that, but we'll get to that. Here's fluorine. 1, 2, 3, 4. How many dots should I draw for fluorine if it's 2-7?
9.
Well, I always draw the outermost.
7.
7. I'm only drawing the outermost electrons because those are the electrons that are what? They feel the nucleus the least. Therefore, they're the ones that can change in bonding. The ones inside are called a core. They feel the nucleus too much, so they can't change. So we always draw these. Now, because fluorine is a small and sodium is a big, and this is me, I'm strong for electrons. This is my 5th grader. He's getting there, but he hasn't won yet. Okay? What's going to happen is there's going to be a transfer. We're going to yank that electron away. And what we're going to make is a fluoride ion. It's -1. This lost its valence electron, and it's +1. And this would be the Lewis dot diagram for things that are ionic. Okay? And they make crystals. And sodium fluoride is in your toothpaste. This is not covalent. This is not organic bonding. This is not what we're going to do to figure things out. But these are how salts are made. And by the way, because it's sodium +1 in all direction and F -1 all direction, what can happen is we make this. Sodium plus attracts an F negative. F negative attracts a sodium plus. And sodium plus and F negative. And the beat goes on, and party people, that is what this is. I lost some ions. This is a crystal lattice of ions. This is not covalent bonding. This is not molecules. And the formula is NaF, sodium fluoride. If there's one sodium ion to one fluorine. Okay. Let's get to what you're going to do. Okay? Now, what if anytime I put together a big atom with a small, there's going to be a transfer? Okay? Someone strong for electrons and somebody weak. Okay? That was my son. What if I put together atoms that are both strong for electrons? So, because I'm into tug of war in my house, okay, I have me and my brother go at it sometimes. I have this big rope in my house, and we just say, let's go, let's go. What you got? And is there any argument in the house? We go for the rope. It stops arguments, okay?
How big's your house?
Go for the rope.
Wait, do you actually?
Yes. People are fighting, my boys fight. Let's go to it.
So the oldest always wins.
All right.
It's actually a good idea.
The oldest always wins then.
Well, we start. Well, sometimes we can change it up. Like he has to be in socks, and my youngest can be in shoes. You know. All right. There's something you can make it slippery. You know. Yeah. Okay. So in any case, so me and my brother have a tug of war. And I call him my evil brother Mongo, and he's a little stronger than me because he works out. And if you were named Mongo, you would too work out. But in any case, so we have a tug of war. We're both similar strength. He's a little stronger, but we have similar strength. He can't yank the rope away from me. He may pull me over, but we're going to be forced to share. So check this out. All right? When we had sodium, its electronegativity was 0.9. When we had fluorine, its electronegativity was 4.0. That's a huge difference. Now, if I have hydrogen, now you say, Mr. Grotsky, hydrogen's over here, but it's not really with the bigs. It belongs over here with the smalls. You put it over here because it's one valence electron. Notice I said in the video, you're a similar atom if you have the same valence electrons. We'll talk more about that next year. But hydrogen has a 2.2 electronegativity, okay? And chlorine, about 3.0. So they're both high. Chlorine's a little stronger. Mongo and me. We're going to put out the valence electrons. Hydrogen is just a 1. It has 1 electron in the first shell, so that's its valence. Chlorine is 2-8-7. How many electrons do I draw for chlorine?
You could draw
7.
7.
I only draw the outermost. So chlorine gets 1. A hydrogen gets 1. And chlorine gets 7.
Where do you get the 2.2 number?
Yeah, that's what I'm looking
Okay, I am giving you the electronegativity values. You can look them up in table S of your periodic table I'm going to give you. I know you don't have that yet, but I will give it to you. But you don't have to. Check it out. Okay? Clearly the smalls are going to be higher. So I'm just giving you an idea of how similar the strengths are. Okay, I know you don't have that form. So these are just electronegativities. Hey, big atoms have small attractions. Small atoms have what? Bigger attraction. It's a value of attractions. Okay, so chlorine has 7 valence. So I put 1 here, and then I do 7 for chlorine. 1, 2, 3, 4, 5, 6, and 7. Because they're both high, they both have high attraction, no one can pull the rope for each other. So no one gets the magic 8 or 2 in this case by completely transferring. They get the magic by sharing, okay? And what's that look like? Well, by sharing, chlorine feels like it has 8. And by sharing, hydrogen feels like it has 2. So right now, hydrogen thinks it's 2. The element that has atomic number, the element or configuration of 2 is helium. Helium doesn't explode, it doesn't react. It's just 2, it fills the first shell. Filling your outermost shell always makes you stable. And this one, by sharing, fighting for them, feels like it's 2-8-8, which, by the way, is argon, another element that doesn't react. These elements on the outer group don't react because they have all the electrons they need. So that's a co-sharing. These are valence electrons, covalent bond. And we draw it this way in chemistry. H, get rid of this. Oops, that's gross. H, 1 bond to the Cl, and you can draw the lone pairs if you want. That dash is a pair of electrons. Okay? All right, so let's go and do some of this on the worksheet together. It's part of your work of home. Okay? I know I'm going to stop in about 10 or 15 minutes to give time to finish test and or complete the homework, but I'm going to keep going. All right? So now we're dealing with this type of bonding. Why do atoms bond? Because by themselves, a lot of them are unstable. These guys explode in water. Fluorine will kill you. You put sodium and fluorine together, you make sodium fluoride. That's in your toothpaste. Are you guys exploding and dying when you brush your teeth with sodium fluoride?
Not usually.
No, because though in that form, they're low energy. Low energy is stable. In the form as atoms, they're high energy. Okay? All right, so let's do this. All right, so you got the electron dot diagram out. I'm going to connect to this and say screen mirroring now. Engage. All right. Cancel, I don't want that. I want this.
Yeah, some no sugar.
Okay,
It's the sugar.
maybe. This one. All right, so let's just see if we can understand what I basically said right here by filling in the dashed lines. Let's be dashing. When atoms are held by covalent bonds, a blank or polyatomic, now that one you won't know. This is a polyatomic ion. We'll get to this another date.
Oh, the other one.
Okay, what do you think it is? When atoms held by a blank or blank is formed. A
Atom.
atom is formed?
Electron?
Nope.
Molecule.
Molecule. The word molecule means things have covalent bonds, so molecule. What's a molecule? A self-sustaining particle. One H to one Cl, that is one molecule. It's a small one, and guess what? We have bigger ones, like glucose, like amino acids, nucleic acids, DNA. Those can be huge, huge molecules. What are they made up of? Smalls fighting for electrons, and every single atom achieves stability by doing this. Polyatomic ions we'll get to. Okay, electron dot diagrams for individual atoms can be used to construct dot diagrams for molecules and polyatomic ions. Don't worry about the polyatomic ions. The symbol for each element represents the nucleus. Okay, so when I write the symbol for chlorine, okay, believe it or not, it represents the nucleus and the core electrons. Because we're only going to write the outermost, because those are the ones that change, because those are the ones at the lowest energy. So they say kernel here, okay, or core. The kernel means core, so we'll just put core electrons. It's the same thing as kernel. Those are the electrons that are not part of bonding that we don't write. When atoms form covalent bonds, each atom must share enough electrons to fill its what shell? The outermost shell, which we call
Valence.
That's correct. That's why we call it covalent bonding. They're going to use each other's electrons to fill their both of them their valence shell. Covalent, make it mean something to you. With at least a total of 2 or 8. I say 2 because sometimes we have hydrogen, right? Hydrogen wants to fill its first shell that holds 2. And once it does so, it feels like it's helium, which is stable. That is either 1 pair or 4 pairs of electrons, right?
Discovered all the matchings that
Who discovered?
each one of these can.
Yeah, they have. And they did that way before they even had a periodic table. They knew from all their tests, and then when this came out, it started matching things they already had. It's a really cool story. Okay, constructing dot diagrams becomes trial and error. We're going to do that in a second. Process until a reasonable structure is drawn. The following suggestions will help reduce the number of trials. Okay, I don't care about that. Okay, so we just did hydrochloric acid, and here's another one. Let's go on to these guys together. Okay, I'm not going to do the whole worksheet together, but I'm going to do many of these. Okay, so H2. This is a molecule. This is a particle, a small one, by the way, small one. Okay, so here's where I start. I have an H, and I have another H. And I look at the periodic table and say, well, how many electrons does each one have? All right, and I go to my periodic table and I know that, hey, it only has 1 electron. Look under your periodic table. So they have 1. And the other one has 1. Now I'm doing X's and dots to show you whose electrons are each. Hey, this one belonged here, this one belongs here. Why is H2 a great pairing? Why do you think hydrogen exists in nature as H2?
Stable.
Yeah, they can use each other's electrons to both feel like they have what? By covalencing, right? This one feels like it has 2, and this one feels like it has 2. You don't need the circles, but I draw the circles to remind you that this guy, by sharing, these are covalent. Why are they sharing? You have to understand it. They're sharing because they both have the same high strength for electrons. This is not me and my son yet. All right.
Yet.
And when he beats me, I'm gonna retire.
That's you and your brother.
he's gonna pull me out of like the nursing home. Dad, let's go! I remember this. I'm like, all right, son, but I don't know what I can do. I don't care. Here's a rope. It falls down. Who's your son? Okay. Hope he gives me gloves like I do for him. All right, now.
Wheelchair for like.
All right, so these are sharing. Okay, they both feel like they're helium. Okay, let's look at bromine, or bromine, I should say.
Good thing he has an electric wheelchair.
Okay, now where's bromine? Again, periodic table. Forget the size now. Size helps us understand the chemistry, but let's go find bromine, okay, in our periodic table. Oh, fun up here, all right? And so we find bromine.
Alphabet, actually.
No, 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 no. We put this together because what we found? We found that there was repeating properties. Hey, big, small, starts again, but a little bit bigger. Small, starts again, but a little bit bigger. A little bit, there's a repeating pattern. It's a repeating pattern because guess what? F, Cl, Br, and I all bond the same way because they all have what? They all have 7 valence electrons. This one has what? 8. And this fills the shell. That's why these guys are stable. Everybody, and this guy has 2, right? That's why hydrogen wants to gain 1. That's the beauty. You put things in alphabetical order, you take away the beauty. Who do you think is the most reactive atoms? Who are the ones closest to being stable? Yeah? What about this group? Isn't this group 1 away from losing to be stable?
I thought they exploded in water.
That's right. That's why they're so unstable. Who else is most reactive? These guys are 1 away from gaining electron to become stable. These guys can't. These guys can't lose or gain that many. By the way, have you figured out that gold doesn't react very well?
Gold?
Why? Platinum doesn't react very well?
Because it's in the middle.
It can't, right! The beauty is right in front of you. You take that away if you do put things in that alphabetical order.
Then be stable and stable bonds.
Stable means low energy. Things in nature that get low energy will stay that way until you add a lot of energy to change them. That's what bonding is. Hey, a big boulder in your yard is stable. Why? It's not going to blow away or change. Wherever it is, it's going to stay. And if you want to change its state, you've got to add a whole lot of energy to move it. That's what stable means. Stable means low energy. Think of the guy in New York City. Okay? We used to go to New York City by the train station. There's always a couple of guys that got off the train. Yo, I got an album, man. I'm just dropping. They got this energy, right? You take your family away from that as fast as possible, and you don't show what? Eye contact. Yo, what's up? What's up? What's up? Yeah. That is someone you don't know what they're gonna do.
He's gonna get PTSD.
Because one time I was in the city, and I gave that guy eye contact.
Oh no.
He followed me for like 16 blocks. Okay? I'll never forget his name. His name was Cheddar Crispy. Because he said it 1,000 times and he wanted me to buy his album. It was in CDs at the time. And I made the mistake of giving him eye contact. Cheddar Crispy. Okay? Okay. He was unstable. I didn't know what he was going to do, so I took my family, let's get out of the Penn Station, let's get upstairs, get around cops. Okay? We're going to the Christmas tree and he's, yo, ba-ba-hum, yo, ba-ba-hum. It's like $5. I wanted to turn around and just give him $5, but man, I was scared. Okay. So bromide has how many valence electrons? And if you can't see, party people, look under bromide. It is 2-8-18-7, the outermost. So if you see 2-8, okay, 18-7. Who cares? The outermost. So you put 7 dots.
I just put 8. Are you kidding me?
I'm not kidding you. It wouldn't. If it had 8 dots, why would it bond? It's already filled. These guys got 8 dots.
Wait, so what are we drawing here?
7.
So if it had 8 dots, it would move to that table?
If it had 8 dots, it would be in that column already.
What is that?
Look. 1, 2, 3, 4, 5, 6, 7, 8. There's a beauty in this table. So 1, 2, 3, 4, 5, 6, 7. I didn't count very well. I'll do that again. 1, 2, 3, 4, 5, 6, and 7. Okay, another bromide. Sorry.
I thought I did 7 and 7.
Right, correct.
Glowing in like.
And then this bromide has 1, 2, 3, 4, 5, 6, 7. And look at this nice marriage here. This one by pulling on the rope. And this one by pulling on the rope. They both feel like they have that octet, that 8. So party people, that's the Lewis dot. You don't need circles.
I did it all wrong.
Okay?
Is that why lithium batteries are like explosive, like in planes and stuff?
Lithium, that's a whole different thing I can't get to. But how many bonds exist between bromide? Can anyone see why bromide's a great reason why it bonds to itself?
Because they both need an 8.
You're right. And so when they hit each other, it's a perfect match.
What is bromine?
That's why I call it bromine.
Bromide's actually a liquid. It's an element that's a liquid. It's a reddish brown liquid.
I've been
What does it
told
do?
before.
What does it do? It's
It's like chlorine.
pretty toxic. I mean, it's pure. Okay.
Oh, great.
Most of the halogens when they're pure are toxic. Now, how about O2? You guys have known forever oxygen is O2, correct? So why? Check it out. Here comes oxygen. Now, where's oxygen? It's right here. Oh, oxygen is 2 away from being stable.
So they need 2.
So they need to share 2. Now let's do this. Okay? Now you're getting there. And that's why the periodic table is so powerful. It was put together by repetitive what? Properties, but it's telling us a lot more than that. Okay? So there's O2 for those that can't see. Okay? O is in group 16. It's 2-6. So put out the 6 valence electrons. Okay, so 1, 2, 3, 4, 5. I always start with 1 bond, so I put 1 here for 6. I'm going to do the same here. 1, 2, 3, 4, 5, and 6. So I'm going to evaluate this. So what I just did is I wrote the O, which represents the nucleus and the kernel or core electrons. I put the outermost electrons. I have to know that by the last number. And then I'm going to evaluate to see if this thing works by doing my circles. You don't have to. Some people see this already. By sharing, each oxygen feels like it has what?
You only get 7.
Correct. That's not going to work. That's not the correct Lewis dot diagram. So party people, here's what you do in this case. Just like Theo said, we're just sharing 1 more. Don't we've got to share 2? So what we're going to do, party people, is we're going to move this one. Okay.
Well, you only need to share 1 from one side, right? Oh, no, no, no.
Okay.
I am so lost.
And I'll move this one.
Huh?
Ah, someone's got it.
Oh, that's Holly.
Yeah, that's what
I mean, I get it, but what is this?
I got it.
Listen.
I got it.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They both have the outermost.
What are the dots?
The dots are the outermost electrons. These are the valence electrons. These are the electrons that are the farthest away from the atom. Why do we write those? Those feel the nucleus less, so they're going to be part of bonding. We don't draw the inner electrons because they're too close. So we're showing how these atoms are bonding. So party people, for this to work, it needed to share 2 of its electrons.
Are there any stable atoms that you do not need to bond?
Yes.
18, right?
Let me give you an example. Let's go with, did I give you one? Let's go helium. Helium is He. It's, guess where it is? Guess where helium is?
In the 18.
Right. Helium has 2 electrons. It's never going to lose them because it's small, and guess how many electrons fill its outermost energy level? 2. How about neon? Pretty boring. Neon is 2-8. So I draw 8. And neon doesn't bond because it has all the electrons it needs. Looks a lot like what? Bromide, right? Doesn't helium look like hydrogen? Hydrogen is becoming like helium by feeling like it has 2. Neon, bromide's being like neon by feeling like it has 8. Okay, moving on. O2, now we're not done with this. We just saw that there was what? 2 pairs. So party people, watch this. Oxygen
Oh, I have another question.
is double bonding with another oxygen. Because every dash is a pair of electrons. That's a pair of electrons. And that's a pair of electrons. So there are every dash. So oxygen is double bonded. Yes?
Could there be an atom that takes more electrons than that atom takes? Like, let's say one atom takes 3 and another, the same atom that's bonding takes 1.
Yes. Yes, definitely. Right now I'm giving the easy ones. How about
15?
N2?
Nitrogen?
Okay, nitrogen. I start with N. How many dots do I start with?
1 and 1.
2-5.
So 5.
5 dots. So put the 5 dots out there.
Well,
1,
You put 4 out.
2,
5
3, you put all of its valence. Because those are the outermost electrons. Okay, here comes another nitrogen. I'm always going to start with one bond, so I'm going to do the same thing. 1, 2, 3, 4, and 5. Okay, right now by sharing, if I share this one feels like it has 1, 2, 3, 4, 5, 6, right? This is not even close. For those that can't see it, I'm sorry, I'll draw it in a little neater. Okay, so if you notice, party people, by sharing, this feels like it has how many? 6. It only gained sort of 1 more. How many more does it need to gain to be like neon, who has 8 on the outermost? 3. So it's got to share 3. Oxygen had to share how many? So it had 2 bonds. So how many bonds do you think N has? 3. So watch what I'm going to do here. I'm going to move this one over. I'm going to move this one over here. Now, if I do 2 bonds like I did for nitrogen, now nitrogen feels like it has what? 1, 2, 3, 4, 5, 6, 7. Better, but not quite 8. So what I'm going to do is have 3 pairs.
What about the other nitrogen? Like,
Yeah,
They-
what about him?
We'll get to him quickly.
What are you talking about? He's doing the same thing. I just took one from here and moved that there. And I took,
Yeah, they both kill it.
Did they just do it on their own, or?
wait,
Yeah.
Doesn't the other one become like, doesn't the other one want 8 too?
yes,
It does.
Yeah,
Look,
they
it's
check it out.
It has 8.
They both have
No,
it.
Look, they both steal the other one.
Oh.
They're both fighting for the same electrons. No one's strong enough to yank them, so
How do
they're
they both
forced
get it?
to share.
Why is this
They
one
can both
not?
get it.
It's 2.
How'd they get it?
It's 2.
They're nuclear charged. They're highly attractive. They have to collide first.
No, how are they both getting the electrons?
Because they
Only
already
one of
had
them.
them. Each one already
No,
had
no,
them.
no, no. How are they getting more electrons if both of them are using them?
They're transferring like they're sharing.
Because
They're-
they're both using
they're
them.
sharing.
If me and you have the same strength, and the electrons are the outermost valence, you can't pull my rope away, I can't pull the rope away. We're forced to share the rope. Let's say the rope is 1 more electron.
But part of the rope is mine, right? If-
Right, but
You're both
the
using
entire rope is being shared. So I, by pulling on these simultaneously, what's a bond? These highly attractive nuclei are pulling on these electrons. That's what creates the bond. And if there's more negatives in between them, stronger the bond. There's 3 bonds there. So nitrogen. By the way, this is important in biology. I'm going to stop here for a second, and I'm going to give you some time. Nitrogen is triple bonded.
Oh, yeah.
And because it's triple bonded, plants can't use the nitrogen in the air. Nitrogen should be a small, it's highly reactive. Look, fluorine kills us. Oxygen we have adapted to use, but nitrogen is the 3rd most attractive element. It should be pulling electrons all over the place and messing with us. Because it's triple bonded, it's stable in the air. We breathe it in and breathe it out. The problem is that plants who need nitrogen can't use it because it's got the triple bond. So we need for the nitrogen to be fixed. You guys study nitrogen fixing bacteria or talk about that? There needs to be organisms in the environment who can break this so that the plants can utilize it. We learned a long time ago that's why we use fertilizer on our plants. Fertilizer has the nitrogen broken into single bonds that the plants can absorb. Okay? It's called fixing your nitrogen.
Can we try 15?
Wait, how is
So
there
wouldn't that be
3 bonds
dangerous?
if there's only,
15 is a
if
big
you only
number.
do 2?
Or big-
Pairs of electrons that are shared. 1, 2, 3.
Oh.
Okay? Okay, let's do this one. And this is the last one I'm going to do together.
No.
Yes.
I want to try 15.
Oh God.
Okay?
Oh, there's
Oh,
4
Buddha.
now.
Here's carbon.
What do we do?
Now, the one that has multiple, now carbon is that organic compound, is a reason why. Carbon has how many valence? 2-4. So it has 4 dots. It's going to be the center atom. And I know that because carbon has 4 valence electrons. It needs how many more to be stable? 4. How many bonds do you think carbon likes to have? 4. Beautiful. How many bonds does nitrogen need?
3. Nitrogen is
Good. 1, 2, 3. Correct. How many bonds does oxygen need? Good. How many bonds does hydrogen need? Right. So if hydrogen just needs 1 bond and carbon makes 4, look, I can cheat.
Wait, so does it go
1,
forward?
2, 3, 4. H has 1 only. Now, if I don't want to cheat, watch this. Here's H. What does H bring to the table?
one more.
Right. I'll just change the color. Maybe not. And a pair of electrons is what? A bond.
Nitrogen is a real
Okay.
thing.
Now, let's stop for a second. Okay, I'm gonna draw an amino acid. Darn it, I didn't have it up here. I'm gonna draw you an amino acid. Get this off for a second. Here's the basis of amino acid. Carbon double bonds to an O. Can you guess how many electrons are being shared? Double bond.
Which ones?
Carbon double bond to an O.
So
If it was a single bond, it would just be that, right? It's a double bond, though. In fact, let me draw it you this way. Carbon double bonds to an O, to another O, to an H. This bonds to another carbon. This bonds to an H. This bonds to, let's say, we'll say an R group. This bonds to an N.
What's an R group?
That's a attaching group. Let me help you. Okay, now, look at this for a second. Watch, party people. How many bonds does oxygen have?
One.
What is this?
Or two.
How many bonds does oxygen have? This is called an amino acid. Party people, this is an amino acid. Who found the amino acid? At the-
The guy.
What's his guy?
Steven.
Stephen Miller.
Not Steven.
Steve?
Steve Miller.
No, that's...
RNA hypothesis guy.
No! Well, he was in there, yes.
Joseph.
Stanley Miller.
Yeah, that
Steve
guy.
Miller is the
That's the
guitarist
guy.
and the singer for the Steve Miller Band, okay?
Oh yeah.
So, here's an amino acid. Stay with me. How many bonds does oxygen have?
Two.
2. How many bonds does oxygen have?
Two.
How many bonds does carbon have? 1, 2, 3,
Four.
4. How many bonds does hydrogen have?
One.
How many bonds does hydrogen have?
One.
How many bonds does nitrogen have?
Three.
Three.
How many bonds does carbon have?
Four.
Four.
Wow.
That's pretty cool.
Okay, it's so damn cool. Okay? Now, let me draw it out this way. Okay? Carbon, double bonded to the O. Single bonded to another O. Single bonded to an H. Single bonded to another carbon. Bonds to an H. Bonds to an R group, you'll talk about that in no time. Bonds to an N. But N makes only what? 3 bonds.
What's the R?
That, the rest of an organic molecule, we'll talk about that. Okay?
Ours another group.
You will. You have to stop with the idea that whatever I teach you, you're going to grab in 2 seconds. Middle school is over. Middle school is over where the lessons were so easy, you can just say, okay, I'll do that right now. I'm going to show you fructose. Okay, let's do fructose. Fructose. Okay, which is a sugar. Os means sugar. Stay with me. Okay, and that's the last thing I do. Okay, I don't expect you to get everything, and you're not. So you have to stop with, I don't get everything right now, so I don't understand it. This is not middle school.
Would you be offended if I don't do AP Chem?
No, you can choose anything you want to do. Okay, now, I know that my H's are light. Okay, so let's darken this up. Nope, it became bigger.
What's fake sugar then?
Not sugar, it's called a sweetener.
Like glucose?
Okay, so let me draw in the H's because, hey, I'm tall. I know it's hard to see. Okay, can we explain the structure
Oh, why?
in terms of what's happening? These are all nonmetals. This is a cyclic. Okay, how many bonds does carbon have?
4.
1, 2, 3, 4. How many bonds does oxygen have?
2.
1, 2. Oh, this oxygen. 1, 2. Okay,
Wait,
this,
that one has 3.
Yeah, what?
That one has
No,
3.
I don't think you're supposed to do the one in the middle.
Yeah,
it's
that's
not, you're right, they're not bonded. I can't, there was a mark there. Thank you very much. So 1, 2, 1, 2. Carbon has how many bonds? 1, 2, 3, 4. This carbon has how many bonds? 1, 2, 3, 4. This carbon has 1, 2, 3, 4. How many for O?
Two.
1, 2. Okay, you get the point here. How about water? Why is water H2O? How many bonds does O have?
2.
How many does H have?
1.
Done. What's the Lewis structure look like? Oxygen has 6, 1, 2, 3, 4, 5, and 6. Each hydrogen brings 1. Why it's bent is a different story from a different day. And it stops there. That's a molecule. Why does it stop there? Every element is satisfied. Hey, let's do this another way. Put in the electrons. Hey, pair of electrons here, you get the point. Okay,
How much,
so
how much does a molecule make?
I'm done. Okay,
Because we have 2 minutes.
so your job
At like 10.
is in part to finish this, and you got some lectures to look at and finish and continue on. Okay, the rest of the time is yours. For those that want to keep working on your test, you can. If I didn't give you enough time,